So this is the result. What do we have? The integral solution is dotted. Let me just make this brighter. So the integral solution is the dotted lines. And then we have two different Prandtl numbers, and they're compared with the self-similar solution. So that's the exact analytical solution. So how do we do? I guess the Prandtl number of 10 is really good. We're basically right on top of itself here. And then the Prandtl number of 1 is still pretty good, but maybe not perfect. So I guess the question is, why is Prandtl number of 10 better than Prandtl number of 1? Well, Prandtl number of 10 is going to have the valid velocity solution sort of covered more completely. So it's a little bit accurate, more accurate there. But it's not bad. You're getting some model that you can then put to some good use. Okay, let's see. What else do we have? So maybe one more slide here. Let me just put this back. If you have a situation where what we've done so far is we said, in my temperature model, I'm saying Ts minus T infinity is a constant value. So that is saying I have a constant temperature solution, or I have a constant surface temperature solution. You know that that's not always the case, right? You know that you could have potentially a constant heat flux, or the reality is always somewhere in between those two things. So if we wanted to reformulate the model where we had a constant heat flux, but allow temperature of the surface to vary, what would we do? Well, it is actually a lot easier than it seems like it would be. What you need to do is you say, I'm going to use my Fourier's law relationship here. That's coming from my assumed temperature profile. This relationship gives me Q dot double prime S, which previously we assumed was varying, and Ts minus T infinity, which previously we assumed was constant. If I go through and I solve this in terms of Ts minus T infinity, and then substitute this relationship in anywhere I see this, that lets me express this in terms of a constant heat flux. So it's really simple, but lets you flip things around, right, and change the nature of the problem. So let's just do that really quickly. This is our last thing here. So what I would do is substitute in, let's see, down here, so dx of u infinity times, now instead of Ts minus T infinity, let's use that Q dot definition. So it'd be Q dot double prime S times delta T over 2K. Then that's times delta T times 1 over 6 square root of Prandtl minus 1 over 30 Prandtl. Okay, and then that's equal to 1 over rho C times, we can leave our heat flux as it was on the right-hand side, Q dot double prime S. So this ODE now, nowhere in this ODE does Ts appear. We're assuming a constant heat flux, and we can evaluate the integrals based on that. So now Q dot comes out is constant. This stuff comes out is constant. And then we can solve the ODE that way. So that would end up looking like this, which would be 1 over 6 square root of Prandtl minus 1 over 30 Prandtl times, let's see, dx of delta T squared equals 2K over rho C u infinity. So how do we solve that? I guess we're trying to take the integral of d delta T squared. That's fine. I guess we're just, you can bring the x over to the right-hand side, do the integral for d delta T squared. That would give you what? So rearranging becomes like this, d of delta T squared equals 2K over rho C u infinity. I guess I bring a back into this because it makes it easier, times dx. Okay, then integrating that becomes delta T squared equals 2kx over rho c u infinity times a. Rearranging delta t equals square root of 2kx over rho c u infinity a. H would then be the square root of all that stuff, so 2k rho c u infinity times a over x. And what we want to do, I guess we could, this is the solution, right? So this is our heat transfer coefficient, h, I guess we call h sub x as a function of x. And we can compare that to the constant temperature solution, which was slightly different. It was just, so constant temperature was h equals square root of k rho c u infinity a over x. So it's almost the same thing, right? The only difference is the square root of 2. So that's telling us if I go to a constant heat flux condition, my constant heat flux boundary heat transfer coefficient is about a square root of 2 larger than constant temperature.